Welcome to UVU CS3060 Lecture 10.1, where we discuss demand paging. Virtual memory's main functionality is called demand paging. So consider for a moment that we have two programs, two processes in main memory, program A and program B. Now, before, we could just simply swap this entire program out and swap the entire program in. But with demand paging, what we do is we just load the pages necessary into memory and use them. Thus, instead of using several frames of memory, we only use one frame at a time as necessary. This allows us more programs that can be in memory. It requires less I/O because we're not making 7 accesses to storage. We're only making 2, one for each frame, the one that's swapped out and one that's swapped in. Gives us memory for more users, faster response time. It is very similar to paging with swapping. Now, when a page is needed, there will be a reference to it. Now, that reference to that from that page can be set to invalid or not in memory. If it's invalid, then that's an illegal access. That means that page hasn't been allocated for the process by the operating system. But if the page is marked as not in memory, then the operating system, instead of exiting that program, will instead perform a disk access and load that frame of data into memory, and then allow that program to continue. So there is a concept called a lazy swapper, and what the lazy swapper does is it never swaps a page into memory unless the page will be needed. In the case of a lazy swapper, when a program is started, only the first page of instructions is loaded. The rest of the program remains on disk until another page is needed. And the same thing is true with the data. You don't load the global data, the strings, until those strings are absolutely necessary, at which point it's considered not in memory, and you just bring it into memory by loading that particular frame from the program. Now, the swapper is generally called the pager in most operating systems. So let's go ahead and see what we can do with the pager. So some of the things a pager will do is it will guess which page will be used before swapping out. So if we have a program in memory and some of those pages of that program have not been executed, the pager may want to swap those particular pages to disk. Now, how do we determine which set of pages are useful for us? Well, this is where we actually use the memory management unit to implement demand paging. So if pages needed are already memory resident, then it's just a regular memory access. But if a page is needed and not in memory, then we need to detect and load the page into memory from storage without changing the program's behavior. The program should never notice that it was not in memory in the first place. This is something where we have swapping without the programmer needing to be involved. It's all part of the operating system. Now, we've discussed a little bit about the page table, and we have here a page table that defines logical memory for us. Now, the logical memory is allocated for a particular process. There's part that is allocated, and there's part that is unallocated. All the pages that are allocated for a particular process in the page table will have a special bit set indicating that page is valid. All the other pages will be invalid, and any access to that will cause the memory management unit to fault. So so our memory management unit needs to be able to check these bits and determine what's a valid page or not. So here we have logical memory of a process. Now, this is a process that has 8 pages allocated. And in our page table, we have page 0, page 2, and page 5 in physical memory, so that whenever those accesses are made, it's a very quick translation of the memory management unit to go to the appropriate frame within physical memory. But all other pages are marked as invalid. So let's say, for example, that the instructions have gone through all of page A and we're about to run an instruction on page B. Well, page B is invalid. That would cause the memory management unit to fault. Now, we do have page B out here in storage, but not in physical memory. So the question becomes, how do we manage this so that we can get the right page from storage into memory? Well, when that reference happens and it's invalid, we create what is called a page fault. This is where the memory management unit sends an interrupt to the operating system, telling the operating system something went wrong in memory. Now, we've discussed how the page fault would normally shut the process down if that process was trying to access memory that did not belong to it. But now we have a problem where valid pages are not in memory. Now, the invalid bit will cause a page fault, so the operating system will note that while that page may not be loaded into physical memory, it is found in storage. So because it is not in memory, it's going to go ahead and find a free frame. It's going to swap the page into the frame by scheduling a disk operation. So it's going to load that page into a frame of memory. It's then going to set up the page table now so that that particular page is valid, and then restart the instruction that caused the page fault. If this is a valid page, has been allocated for some purpose, then instead of just simply shutting down the program, now we have new steps that we take in order to accommodate our virtual memory scheme. Here's a diagram that kind of goes through the steps. So here we have the CPU performing a load operation. Step number 1 goes to the page table. And when the memory management unit sees this invalid bit, it sends a trap to the operating system. Now, do note that these instructions do not have operating system functionality at this moment. This is just simply the program running through and saying, I need data from memory. Well, the memory management unit faults to the operating system. Now, if this is an invalid access, the operating system simply aborts the program. But if it is valid, it goes on to step 3, where it finds the page on the backing store, whether it's the actual program file or whether it's actually in a swap space of some sort. It loads that page into a free frame of physical memory in step 4. The operating system then rewrites the page table so that this particular page is valid, and then in step 6, that instruction is re-executed so that the memory access can be attempted again. It will be valid, it will go to physical memory, and everything will work just fine. So there are some things to think about when it comes to demand paging. We can actually have an extreme case where a process has no pages in memory, meaning that nothing is loaded until it is absolutely needed. We call this pure demand paging. Anytime we try to access memory that is on disk, but not in physical memory, We call this demand paging, where it's requesting that page from the disk. But in pure demand paging, nothing is loaded first. Now, this can be considered kind of slow, so it's usually best if a pager goes and actually loads multiple pages at once, thus eliminating any potential delay when it comes to accessing instruction. Now, some instructions will actually access multiple pages. On the IBM S390 architecture, there are move instructions that will move multiple pages of data from one memory location to another memory location. Clearly, this is going to take multiple pages. So how do you manage those particular pages? Well, that may be a case where there will be multiple page faults and that need to be handled. We need to be very careful in those situations, because if a copy starts happening and then a second demand paging happens, do we redo the first page copy? Is that going to cause problem? This is very, very painful whenever you're dealing with vector calculations, where multiple memory locations can be used to perform a calculation. You can't redo some calculations by running the instructions, and so it's imperative that all the pages are in memory before the instruction gets loaded. We call this locality of reference. Of course, it's very important that there's hardware support for demand paging. Page table has to have a valid-invalid bit. We have to have some sort of swap space. And then we have to have the ability to restart an instruction. And again, this, as discussed earlier, what happens if we have a block move, especially if we have overlap between the two blocks? If data is going to be copied from this upper left-hand corner to the lower right-hand corner, if we have a page fault, do we recopy that data? Is there going to be issues when we do this? Do we restart the whole operation? This can be very tricky, and the operating system needs to be able to handle this appropriately. This brings us to the end of Lecture 10.1, where we discuss demand paging.